Hello there, Mr. Sutton with the AB Calculus 615 Extra Practice Number 1 solutions on integration with respect to y. For this problem, I want to find the area of the region enclosed by these three lines here. So let me start by graphing this out. On my calculator, I've entered all of these in my y equals. Let me just do zoom 6 because I have no idea where these things intersect. So there's the first line, there's the other line, and there's our horizontal line. So we have this little triangular region in here that we're trying to find the area of. Now if I do this with integration with respect to x, which is kind of what this is set up for initially, I'm going to end up with two bottom functions, which means I'll have to split the integral up, which is kind of annoying. So I would instead like to do this with respect to y. So if I want to integrate with horizontal distance strips instead of vertical ones, I'm going to just rewrite these in terms of y. So for this first one, I'll just divide both sides by 2, and now I can write x equals y over 2, or f of y equals y over 2, or 1/2 y. For this next one, I'm going to just subtract 4, and I can write g of y equals y minus 4. And I still have that horizontal line kind of hanging around. Now that I've done that, I need to also find my limits of integration. We're going from y equals 4 on the bottom because of our horizontal line to whatever y value this is up here. I'm not really sure off the top of my head. It looks like it's probably going to be 8 if I count those up, but let me just go ahead and find it on the calculator. So let me do second trace and option 5 intersect, and I'll just have to be careful about this because there's 3 functions. So I press enter once for this first line, enter again for this other line, and then enter a third time. Gives me an intersection at y equals 8. So f of y and g of y equal each other at y equals 8. Therefore, to find the area now, I just need the integral from 4 to 8, and these are both y values now, of, well, it's going to be right minus left. So that is going to be, let's see here, which one is this one, f of y, this is the right function coming from the origin. And then g of y is this left function here. So I'm going to have f of y minus g of y dy. Time to do that on the calculator. So here's what this looks like on the calculator. I've got f of y, which is 1/2 y. And I'm going to do all of these with x's because that's how the calculator rolls. And then I'm going to subtract y minus 4. And I'll write dx instead of dy because I'm doing everything with just the x variable. Press enter, and that's, hey, exactly 4. Nice. For this problem, I want to find the area enclosed by x squared, 2x, and the horizontal line y equals 1. We just want the area above 1. Let me start by graphing all these. So I've got all these in my y equals. Let me just do zoom 6 to see what it all looks like. So there's my parabola, my line, and that line as well. And I could probably zoom in a little bit. Let me do window, and I'm going to go from 0 to, let's go from 0 to 4. Zoom fit on that. See what this looks like. So parabola, line, and other line. So we've got this little sliver of space in here that we're trying to figure out the area of. Now, the way this is set up, if I integrate with vertical strips, integrate with respect to x, I'm going to have 2 different bottom functions, so that's going to require two integrals. That's kind of annoying, so I'm going to do this using horizontal distances and integrating with respect to y. So to do that, I'm going to have to rewrite all these functions in terms of y. This first one's not so bad. I just square root both sides, and I have f of y equals the square root of y, or x equals square root of y. For this next one, we just divide both sides by 2, so we can write f of y equals y over 2. We've still got this line kicking around here. I also need to find my limits of integration. On the bottom, I have a y value of 0. On the top, I have wherever these intersect. It looks like 4. Let me just quickly plug that into these to make sure I get the same thing. So at an x value of 2, we get 2 squared, which is 4. 2 times 2 is also 4. So these things definitely match up at y equals 4. So I'll say that these two functions equal each other at y equals 4. So then I have the integral from 1 to 4 of, and now I have to do right minus left. So that's going to be this square root this, I guess you can think of this as a horizontal square root. So square root of y minus 1/2 y, or f of y minus g of y dy. And let me do that on the calculator now. So here's what this looks like on the calculator. I'm going to use x's instead of y's. My calculator's just going to have to roll with it. And pressing enter, I've got 0.917. For this problem, I want to find the area of this enclosed region. Let me graph this out to see what I'm dealing with. So here's what I've entered in my y equals. Now you might be saying, wait a sec, Mr. Sutton, these are functions of y, not x. And yeah, I got that. But I'm going to enter these in terms of x anyway, because I'm going to use the pattern of something squared minus 4 times something to help me actually graph these things out. So what I'm going to do is I'm going to take each of these and plug them into my draw inverse capability on my calculator. So let me quit out of here now. And let's see, I have no idea where I'm going to be. So let me just zoom 6 right away just to get a window from 0 to 6. And I've got some other, so these are the vertical versions of these. Let me graph these horizontally now. Let me go back to y equals and deselect these. I don't really want the original graphs. Quitting out now. Let me do second draw, so second program here to get my draw menu. Option 8 is going to give me draw inverse. And then we do alpha trace y1. So this is actually going to sketch out y squared minus 4y. I won't be able to interact with it, but I'll at least be able to see what it looks like. And then let me quit out of there, and I'm going to yank my input from before and do a draw inverse on alpha y2, alpha trace y2. So there's my other sideways graph. So this little region in here, this is what I'm trying to figure out the area of, this little spot in here. Now, if you're doing this vertically, it's going to be a huge pain. The bottom and top functions keep changing around, so it looks like we're going to have, let's see, 1, 2, like possibly 3 different integrals that you're going to need for this if you do this with respect to x. And you're also going to have to express these in terms of x instead of y. This is really set up to integrate in terms of y, so let's go ahead and do that. To do integration with respect to y, I need to figure out my limits of integration. I need to know where these things intersect. And it looks like they intersect at 0 and 3, but I'm not really sure about that. So here's how you can find that on the calculator. So going back to the calculator, I'm going to go to, let's see, my draw menu. So second draw, and I'm just going to clear out those drawings. I don't really want to look at them anymore. I'm going to go to my y equals, and now I'm actually going to reselect those functions in terms of x. I can't find intersections with drawings, but I can find them with regular functions. Although these aren't really the same as these functions here, if I find the x values where these functions intersect, that's going to match up with the y values that these functions intersect at. So let me graph these out again. So zoom 6. So there's the first one. There's the second one. And now let me just figure out these x values. So second trace, intersect, enter, 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 close to that first intersection, and we do indeed intersect at 0. This corresponds with the y equals 0 for these graphs here. Going back to my grapher, let me do second trace, option 5 again, and we'll move over to this other intersection place. Enter, 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 and that's an x value on here of 3. That corresponds to a y value of 3 on this graph. So we see that these intersect at 0 and 3. 0 and 3. So that means the area is going to be the integral from 0 to 3 of, and now I have to do right minus left. So let's see here. Which one was which? Well, one of these has a positive y squared and is going to open to the right. This one opens to the right. This one that has the negative y squared is opening to the left. So this is going to be g of y minus f of y dy. And let me do that on the calculator now. So I did math 9 to get my integral. I'm going from 0 to 3. And I've already got g of something entered in my calculator in terms of x. That's in y2. So let me do alpha trace y2 minus, F is just entered as y1, so alpha trace y1. And we'll do dx, since those were actually entered both in terms of x. Pressing equals, I get 9, and I'm going to go with that. For this no calculator problem, they want us to find the volume of the solid of revolution when this area in this picture here, and also between these curves that they've given us here, is spun around the y-axis. So since I'm going around the y-axis, I'm going to need horizontal y-axis integration. That means I need to express this y equals x cubed here as a function of y instead of x. So this is going to be, if I cube root both sides, f of y equals the cube root of y, or x equals cube root of y. And now I also need my area of my cross sections when I spin this thing around. Since the axis of revolution, the y-axis, is one of the boundaries of this region, that means since it's flush against that axis of revolution, I can use pancakes, I can use disks as my cross-section model. So I'm just going to write a of y equals pi r squared for that. And my radius is just going to be the distance between my axis of revolution and this outer boundary, which is given by the cube root of y. So I can write pi cube root of y squared. Since I'm doing this by hand, I'm going to simplify this at some point. And now seems like as good a time as any. So let me call this pi times y to the 2 divided by 3, 2/3. So now to get the volume, I'm going to need the integral from, we're going from bottom to top, so 0 to 8, this is 8 up here, of this expression right here, pi times y to the 2/3 dy. And now I have to take my antiderivative by hand. This bumps up to 5/3 for the exponent. Multiplying by the reciprocal, we've got 3/5 times pi times y to the 5/3. So I'll call that 3 pi over 5 y to the 5/3, evaluated from 0 to 8. Just to make my life a little bit easier here, I'm going to yank this 3 pi over 5 out. And inside, in the parentheses, I'm going to have 8 plugged into this minus 0 plugged into this. So I'm going to have, let's see, this is going to be the cube root of 8 to the 5th power minus the cube root of 0 to the 5th power. We've got all constants, so you could actually just stop here. If you want to simplify this, however, we know this 0 term is just going away. In here, the cube root of 8 is really 2 to the 5th power would be 32. So we've got 3 pi times 32, which would be 96 pi over 5. On this problem, we want to find the volume by revolving x equals y squared and x equals 1, the region between those, about the line x equals 1. Let's start by graphing this out. In order to do this, I'm going to use my draw menu. So I'm going to start by, let's see, seeing if I have anything in y equals. Let me clear that stuff out. And let me just do zoom 4 just to get my window all set up. All right, now I'm going to quit out of there. And I am going to do second draw, so second program, option 8. And let me just draw the inverse of this, so I'm just going to write x squared instead of y squared. And that gives me this sideways parabola. Now I'm also going to draw this vertical line at x equals 1. So go back to the draw menu, x out, second draw, and vertical, option 4, and then 1 for the x value. And there's a picture of what we're dealing with. So I want to take the region in here, and I want to revolve it around x equals 1, so that's actually the same line here. So how can I do this? Well, one thing I need to make this happen is I need functions expressed in terms of y, which we actually already have here, so that's good. We also need to know our limits of integration, the bottom and the top endpoints here. So to find those, I'm going to set y squared equal to 1 to see where these two functions intersect. And we see very quickly that plus or minus 1 are the two y values, which we could kind of read off the graph here anyway. So for my cross sections, because my axis of revolution is also one of the borders of this shaded region, I'm going to have disks as my cross section, so pancakes here. So I'm going to write a of y equals pi r squared, and then my radius is just the distance between my axis of revolution and this other boundary of my bounded region. So in this case, that's just going to be 1 minus whatever y squared is. And that whole thing is being squared. For the actual volume, I have to take the integral from -1 to +1 of this a of y dy, and now I'm going to let the calculator do the rest for me. Just to set things up a little more cleanly on my calculator, I'm going to put this whole area function in y1, so I have pi and then 1 minus x squared squared. It's all right if you put x in here, your calculator will figure it out. So xing out of there, let me do math 9, integral from 1, or -1 rather, to 1, and then let me just do alpha trace to pull up my menu. y1 is what I want, and then dx, and that comes out to about 3.351. For this problem, I want to take the area bounded by these curves here and rotate it about the line x equals 4 to form a solid, and then find that volume. So let me start by graphing all of this out. So the setup for these graphs is pretty straightforward. We have a square root function and a horizontal line going through 2. Let me just do zoom 4. That should give me enough of what I need to see here. And then we have also the y-axis forming the other boundary. So this is our bounded region in here. It's this triangular-ish kind of shape. And then we want to rotate that around the line x equals 4. So let's see, 1, 2, 3, 4. There we go. All right, and so because we're doing this as a horizontal revolution, we need to integrate with respect to y. That means I need to turn this function into something that has y as an input rather than x. So let me just isolate x by squaring both sides. We get x equals y squared. And this is the kind of function now that I can use in an integral to find this volume. Some other things I need my area cross-section. I also need the limits of integration. The limits of integration are actually pretty straightforward. We're just using the y values of this bounded region. So that's going from 0 to y equals 2, and they gave us that one. So now we just need the area of the cross-section. Since I have this big space here between my bounded region and the axis of revolution, that means I'm going to need to use washers, donuts, for the area on this one. So I'm going to write a of y equals pi times big R squared minus little r squared. The big radius, that's going to be the distance between my axis of revolution and the part of the bounded region that's further away, which is just the y-axis here. So we've got 4 minus 0, which is just 4. So we've got 4 squared. And then for the little r here, that's the distance between my axis of revolution and the closer part of the bounded region. So that'll be 4 minus y squared. And now at this point, all I have to do is put this on the calculator. So I'm going to have, for my volume, the integral from 0 to 2 of this a of y dy function I just wrote. So let me show you what I'm putting on my calculator. I'm doing the whole area function in y3. So I've got a pi, parentheses, we got my 4 squared minus, and now we have a squared parentheses here with 4 minus x squared in it. And I'm using x instead of y because if I do dx on my integral, my calculator will just do what I need to do here. And then close that parentheses. Let's quit out of there now. And let me do math 9 for integral from 0 to 2. And we'll do alpha trace y3, that's where I just stored that function, dx. And this is all coming out to 46.914. For this one, we want to find the volume of the solid revolution when the area between these curves is spun around the y-axis. So let me start by getting a visual of what's going on here. To do that, I'm going to put some things in my y equals. So I've got, of course, y equals 4, horizontal line. I can graph that out. I also put in square root of x minus 1. Now that's not quite the same as square root of y minus 1. So I'm going to deselect that graph because I don't really want to graph it. But I am going to use the structure of this, square root of something minus 1, along with my draw inverse function to graph what this really looks like. So let me do zoom 6 just to get my horizontal line on there and get a good window. And now I'm going to quit out of there. And I'm going to do second and then program, so second draw, and option 8 down here, draw inverse. And then I'm going to put in y1 where I stored square root of x minus 1 to this. When I do that, the way my calculator reads this is, oh, you want me to draw square root of y minus 1. Now if I press enter, it gives me this sideways square root kind of function, and I've got a picture of what's going on. So here's what my graph is giving me. We've got this region inside here, and I want to revolve that around the y-axis. So I need two things at this point. I'm going to need my area of my cross sections, and then I'm going to need my limits of integration. So for the area, since the axis of revolution, the y-axis, is actually one of the boundaries of my bounded region, I can use discs here, pancakes, because I have an area that's flush against my axis of revolution. So I'm going to go with a of y equals pi r squared, and then the radius is just the distance from my axis to whatever the outside boundary of that function is. So this is going to be the square root of y minus 1 minus 0, so just the square root of y minus 1 for the r value here. All right, so I'm going to use the calculator on that stuff in a minute, but let me also get my limits of integration. So at the top we clearly have 4, that horizontal line. At the bottom here, this looks a lot like it's going to be 1, but let's just double check. We can set this stuff equal to 0 to see where it takes on an x value of 0. And if I add 1 and square both sides, I do indeed get 1 for the y value. So for my volume then, I have the integral from 1 to 4 of this a of y dy that I just wrote out. Let me go back to the calculator now. And you'll see here that in my y equals, I've added another function. This is pi times this y1 squared. That's basically this area function here. Now again, you might be saying, well, our true area function is expressed in terms of y, while this one is technically expressed in terms of x, but our calculator's not going to care if we put this in an integral that has a dx in it. It's still going to just treat it as a dummy variable and do exactly to that what you would be doing to this thing on paper. So quitting out of this now, we've got math 9 for integral. We're going from 1 to 4. Alpha trace y3 to pull up my area function. And again, I'm going to use dx. Pressing enter, I've got 3.665, and that's my answer. On this problem, we have this graph here of f of x, which is e to the 2x, and we also have this horizontal line at x equals 1. And they're calling this region between these things and the y-axis here. This is all r. For our first task on this, we want to write an equation for the line tangent to the graph of f at x equals 1. All right, so we're just going to use our general tangent line setup. L of x equals f of a plus f prime of a times x minus a. So applying that to the problem here, the a value here is 1. That's our launching off point for our tangent line. So I'm going to write L of x equals f of 1 plus f prime of 1 times x minus 1. And I can't just leave it like this. I have to actually commit to what f of 1 and f prime of 1 look like. F of 1 is just what I get when I plug 1 into the f function here. So that's e times 2, or e to the 2 times 1, which is just e squared. For f prime of 1, let me first get f prime of x. That's going to be e to the 2x times a tail of 2, so 2e to the 2x. Plugging 1 into that, I would get 2e to the 2. And then we can't forget that we have x minus 1 out there. This is the equation of a tangent line. We have an equals involved here. So we're actually done. We could put this in mx plus b form or something else crazy like that, but why bother? This is algebraically equivalent to whatever they actually have in their answer key. On this part, they want us to find the actual area of R. So if I think about this as going from left to right and doing top minus bottom, I could definitely do this if I integrate with respect to x. So I'm going to go ahead and do that because my function's already expressed with respect to x. So let me do here area equals, and now I need an integral from 0 to 1 of, well, what am I integrating? I'm just going to be integrating this e to the 2x function because this whole area is between that function and the x-axis. So it would really just be this function minus 0, which is just e to the 2x dx. I have to do this one by hand, though. This is a no calculator problem. So this is going to be, if I integrate this, take the antiderivative, this is going to be, let's see, e to the 2x divided by 2. So 1/2 times e to the 2x, evaluated from 0 to 1. I'm going to yank out this 1/2, and inside I'm just going to have e to the 2 times 1 minus e to the 2 times 0. So this is going to be 1/2 parentheses e squared minus 1 if you really want to simplify this. And you could distribute this 1/2 if you wanted to, or put all this stuff over 2, but why bother? Even back at this step, you actually could have stopped because you've got all constants, and it's a free response. For this part of the problem, they're telling us that region R forms the base of a solid whose cross-sections, which are perpendicular to the y-axis, so we're going to integrate with respect to y, those cross-sections are squares, so I guess it could be worse. They want us to write but not evaluate an expression with integrals that gives the volume of the solid. And notice here they said one or more integrals. So it's possible we might need to write like 2 or more integrals. All right, so first off, if I'm going to be integrating horizontally, I'm going to need to rewrite this function here in terms of y. So basically, we just need to get x by itself in this equation. So if let's see, this is really y equals e to the 2x. To get the 2x out of exponent land, I need to take the ln of both sides. So I've got ln of y equals 2x. And then we just have x equals ln of y over 2, or 1/2 ln of y. So I'm going to write this as f of y equals 1/2 ln of y. All right, at this point now, let me get my area of my cross sections. So since we're doing squares, I'm going to have area of y equals s squared. And I'm not going to plug this in right away because I don't have the same right and left functions all the way through this interval. When we start at the bottom, which is where you're going to start if you're integrating with respect to y, your right function is 1, and that doesn't change throughout, but your left function is the y-axis, x equals 0. So for my first integral, if I'm writing out my volume, I'm going to have the integral from 0 to 1 of, and this is just going to be 1, or 1 minus 0 dy. But now, my bottom function changes when I get to 1, and now it's this 1/2 ln of y function. So at this point, from 1 to, let's see, what's the y value up here? E squared. So I'm going to be adding an integral from 1 to e squared. I'm going to have 1 minus f of y dy, and I've actually got that squared. Now over here, I guess I could have squared the 1, but 1 squared and 1, same thing. But here we do need to put the squared in.